to present our ideas about the generalizations of the principle of information causality to the multipartite case. This is a joint work together with Costantino and Raphael. So information causality was formulated in this paper in 2009, and it can be defined as a game between two distant parties, where Alice receives the n+1 random bits, and Bob receives some number from 0 to n, and depending on that number, he tries to guess the corresponding bits of Alice. Let's say if he receives 0, he tries to guess x0. And Alice can send some classical message to Bob, and they are as well they're allowed to share some quantum resources. And what the information causality principle states is that the information that Bob can obtain about their random bits of Alice is bounded by the entropy of the message which Alice sends. And so this principle has two perspectives. One perspective is from the point of view of the communication. It says that actually the quantum resources are useless in this case, or they don't give us any advantages in terms of mutual information. And the other point of view is the point of view of bounding the set of quantum correlations in some larger set of non-signaling correlations. Because let's say if Alice and Bob share the PR box, then they can violate this principle. So today I would like to concentrate more on this perspective. And from this communication perspective, its natural generalization would be to consider many senders and many receivers, and which share some global quantum state, and they are allowed to communicate for some classical network. And here the game is quite similar. So if Bob receives some number which tells him in which bit he is interested in, but this is a bit different from the bipartite case, because now let's say the Bob2 can be interested in the bit of which Alice 1 receives. Okay. And what I mean by this classical network for which they communicate is some set of channels with a bounded transmission rate and some intermediate nodes which perform the classical coding, yes, classical coding. And so from the point of view of these networks, the information causality between the many senders and many receivers would be just this network with additional resources for the senders and the receivers. And what we prove in this case is that actually, again, the quantum resources, they don't give us any advantage in the transmission rates. And how we prove this is through the entropy vector method, which is used to derive the transmission rates for the classical networks. And in this method, we define the entropic cone, which is, let's say, for the set of random variables, classical, we define the some entropic measure, in this case, the Shannon entropy. And then if we consider the vector of the entropies for all sets of random variables, we see that these vectors actually, they form a convex cone, and they are bounded in this space of entropies. And okay, I'll define this cone as gamma. And in the quantum case, it's a bit more complicated, because now instead of just random variables, we have some states which can be reduced states of a larger system. And now we have some restrictions on the possible sets of variables which we can observe, which are the sets of coexisting variables. Let's say we know that the outcome of the measurement and the state on which this measurement was performed, they in general do not coexist. And okay, in this case now, the entropy we pick as the phenomenon entropy, and the quantum entropic cone would be the intersection of these quantum cones for the sets of coexisting variables. Okay, and so these entropic cones define us some possible relations between the entropies of the sets and the subsets, but what we are actually interested in is a certain subset of all these sets, also some variables which we can actually observe at the experiment or which we have access to, and this is called the marginal scenario. And let's say in the case of bipartite information causality, this marginal scenario is just the pairs of the random bits and the guesses and the message. And so having this marginal scenario, we can take the entropic cone and project onto this marginal scenario and get some inequalities, valid inequalities for these for these observables. But what we have additionally as a constraint is the constraint coming from the network of the communication. It's a bit similar to these causal networks, but it gives a bit stronger constraints on the possible correlations between their variables at distinct nodes. Okay, I won't go much into the details, but these are linear constraints on the level of the entropies. Yes. And how we calculate now the transmission rates in the classical case, we take this entropic cone for these sets of variables, we pick the marginal scenario in which we are interested in, we add the network constraint, and we just project this entropic cone together with the network constraint on the marginal scenario. And what is nice about this classical case is that there is a theorem that these rates which we get from out of this method, they are actually achievable. And in the quantum case, it's much more complicated, because now we have, as I said, the sets of coexisting variables, and we have the new inequalities which connect these different cones of the sets of coexisting variables, which are the data processing inequalities. And again, in the case of where A is the measurement outcome on the system A, we have that they're acting locally on the state. We cannot increase the mutual information with some third variable. Okay, and so in this case, the calculation would be to take this intersection of the entropic cones, quantum entropic cones for these sets of coexisting variables, add a network constraint, add this data processing. And in fact, it's not known if these rates out of this quantum network are actually achievable. But what we can say in the information causality case, in this case of multiple senders and multiple receivers, where we have only quantum nodes here next to the senders and next to the receivers. Okay, these are just the notation of the variables which will appear later. So these are the reduced states of each Alice's, and these are reduced states of each Bob's. And there some additional parameter which will appear later is the choice of these Bob's or sinks measurement. And what are the sets of the coexisting variables in this case? Is they come from the sets where Alice performs some operation on her state and creates a message. Then the second one is when the Bob performs some operation on his part of the state and creates some guess. And finally, the third set is there's just a set of these random bits and the guesses. So in this case, yes, the calculation of the transmission rates would be the projection of these three cones together with the data processing, which comes from the Alice performing the measurements, and data processing which comes from the Bob performing the measurement, and the network constraints. Okay, in the bipartite case, we can see it's much simpler. First, we have some set of these random bits which Alice gets, and we have two states for Alice and Bob. And then Alice performs a measurement and creates a message. And this is now their set of variables which coexist together. And then later, Bob again performs a measurement and creates a guess. And this is the third set. And yes, and so applying this approach, we can prove that actually the transmission rates in this case would be just the transmission rates for the classical case. And we can prove this by showing that first the entanglement between all the Alice's on the Bobs, they play no role. And we can see that the only constraint which comes from the shared states of Alice and Bob, they are here in this data processing. And as because we do not put any constraint on the right-hand side, we don't get any additional constraint on the left-hand side. And we eliminate these variables A in the end. So basically, we don't get any information from this cone for this set C0. And the second case, we prove that there's no advantage in sharing the entanglement between the different receivers. And we can see that by looking at the marginal scenario for different receivers. And we can say that if we do not have access to the guesses of different bobs, we can just say that the probability distributions for all the inputs and all the guesses, it factorizes on their probability of input. So there is some, the creating of these guesses can be explained just from some local hidden variable model. Yeah, okay, this is the first part. And then I would like to say something in the second part, in the perspective of bounding the set of quantum correlations from these information principles. And of course, here there is as I said before, if Alice and Bob can share the PR box, then they can violate this information causality principle. And actually, it is possible to obtain the Tyrrell bound from the information causality principle. Yes. And of course, the motivation of finding some multipartite information principles, it comes from this paper, which says that this set of quantum correlations requires multipartite information principles, and as well the paper where they consider the extreme multipartite correlations, which can be ruled out by the bipartite principle, and where they show that almost all these extremal and non-local correlations can be ruled out, except for one, which is bipartite, which is do not violate any bipartite information principle. Well, and then we'd like to consider some symmetric game of Alice, Bob, and Charlie. And each receives some random bit. And depending on this bit, they try to guess one of the bits of the other party. So let's say if Alice gets 0, she wants to guess the bit which Bob received. And if she gets 1, she wants to guess what Charlie received. And they're allowed to communicate through some pairwise messages. So in other words, each party is allowed to get some message from the other two. And of course, the main point that they are sharing some tripartite correlations or some quantum resource. Doesn't matter. Okay, of course, if you consider something like one way of this game, or just one way of the communication, where Alice and Bob create a joint message, then of course there is some of the mutual informations of the guesses for Charlie would be bounded by the entropy of the message. It's just the bipartite information causality applied in this case. Yes, but the question is, if we now consider all these three directions, will the sum be bounded by this entropy of these three messages? It's just the sum of the bipartite information causalities. And the question is not necessarily. And what we can see is that if we can, as a referee, certify that these messages were created somehow space-like separated, then there is no relation, there is no direct link between the message of, let's say, a joint message of Alice and Bob and message of Bob and Charlie. And then we say that all these separately information causality terms, they are valid, and the sum is bounded by this sum of the entropy of the messages. And okay, we can say that if they send one bit, then it's bounded by 3. But now, if we say that one message can be in the causal feature of other two, then actually the bound is no longer true. The sum is bounded now by 4. And this can be actually seen just on the simple example where these Bob and Charlie, they just wait to receive their message, and only then they create the joint message for B and C, and then they can obtain this value of 4. And okay, the third more general case is then when these messages are realigned somehow in the causal feature of one another, and then this sum is bounded by something like 4.3. Okay, this is some numerical bound. And okay, I would like to argue that this is not in principle a bipartite information causality, because first of all, there is no somehow direct cut between parties, and the second of all is that information causality itself, like for one bipartition, it doesn't hold in this case, because we are in this case, let's say, because we are as a referee, we don't know how these messages were created, because let's say the information causality between Bob and Charlie and Alice, it doesn't hold in this case. So this is something like a not, I would say, not a bipartite principle, yes. So, but okay, in this case we have more questions than answers, and yes, yeah, I would like to just thank you at this point. Yeah, I have plenty. Okay. Yes.